Hi, this is the first part of Lecture 20 for COS 217 on Assignment 5, Assembly Language Programming and Testing. Now, there is a second part to this lecture on using GDB with assembly language, and you can find that as a separate video on YouTube linked from the course schedule page. So assignment 5 is going to be where you apply your knowledge of assembly language that you've been gaining over the past couple of weeks to writing actual assembly language code. So this is going to come in two parts. First, you're going to pretend that you are the compiler, and you're going to translate a C function that we give you into assembly language. Also, as part of this part, we're going to be asking you to generate sample data, that is testing data, to make sure that you got that translation correct. In part 2, you're going to be writing not an entire program, but a single function, but the name of the game is going to be to beat the compiler. You're going to try to write that function in assembly language so that it runs as quickly as possible. And if you use the right tricks, in fact, you are going to be able to beat the compiler pretty substantially in terms of how fast you can make that one little function execute. So let's start with part 1. This part is going to be about implementing the WC command. Now, WC is a standard Unix utility that stands for word count, but in fact, it actually prints out 3 different statistics about a piece of text. So for example, if you run it on this little proverb, then it'll print out 3 different numbers: the number of lines, the number of words, and the number of characters. The number of lines is defined as the number of sequences of characters separated by new lines. Number of words is defined as the number of sequences of characters separated by spaces or space-like characters. And the number of characters is, of course, just the total number of chars in the entire file. So here is the code that you are going to be responsible for translating. I'm not going to go over it in a whole lot of detail. It should be fairly straightforward to understand. It has a while that loops over the characters in the input. And then it does a bunch of logic, including a bunch of kind of nested if-else statements, a bunch of increments, and things like that. So a couple of things to notice about this. One is that notice that it uses a number of variables. In fact, it uses 5 of them. They are declared as static variables in the file, and we're going to expect your assembly language version of this to behave in exactly the same way. Also, notice that there's a particular sequence of logic that includes particular nestings of if statements, else statements, some corner cases about exactly what happens at the end of a file and things like that. Again, we're going to expect your code to just directly translate all of that logic. So what we expect you to do is start by taking the C code and generating a flattened version of it using the conventions we showed in Lecture 18. Then generate your assembly code, and we'd really kind of prefer for you to include that flattened C code as comments. And in fact, if you go to office hours, probably the first thing that the preceptor is going to ask is, where is your flattened C code? And does your assembly language code actually implement that flattened C code? Like I said, we want you to use exactly the same algorithm, exactly the same logic. Don't simplify anything, don't optimize anything. There should be a one-to-one mapping between segments of assembly language and statements in the original C code. Use the same static variables, still call exactly the same functions from the C standard library, namely getChar, isSpace, and printf. And, you're expected to generate this code from scratch as opposed to using the output from GCC 217. And the reason for this is partly because we're asking you not to, but mostly because the output from GCC 217, even in its unoptimized state, can be a little convoluted, can be a little tricky to interpret, and so this is, partly for your own benefit. So that's the task. We're expecting you to write this assembly code, but then we're expecting you to verify that the assembly language code is correct by implementing a bunch of test cases. So we're asking you to compose a bunch of data files that perform boundary tests, statement tests, and stress tests. So definitely go over lecture 9 to review what all of these mean. But definitely make sure that you include test cases that test all of the little corner cases. So figure out what happens with very short files, with files that include a single character of different flavors. Make sure that your tests cover all the different things that can happen at the end of a file, running out of ending the file in the middle of a line or in the middle of a word. Make sure all of that works correctly. And then stress tests. And for the stress tests, probably you're going to want to just generate a bunch of text programmatically. So one thing that you may want to do, in fact you probably want to do, is write a little program that just generates stress test data. So you can use functions like rand to help you generate random characters, and definitely read the assignment specification for how many characters and what ranges the characters should be drawn from and things like that. Just in general, how many data files, how extensively do you need to test? Well, at the very least, we'd like you to create enough test cases to exercise every single line of your assembly language code. And in fact, we want you to tell us which test cases exercise which lines of code. But beyond that, sort of pretend that you are going to be grading the assignment. Design enough test cases to really expose what would have been wrong had you gotten the assembly language code incorrect in all the different ways you can think of. So exactly how many test cases do you need? Well, I don't know. It depends on exactly how you design your test cases. All I can say is you're going to need enough to test your code thoroughly. So that's part 1. Now, moving on to part 2, this is going to be about writing assembly language that does arithmetic on very, 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 very large numbers. Now, why would you want to do something like this? Let me give you a motivating application. So, one of the real success stories of modern computers is cryptography, where you can communicate privately, where only the sender and the recipient of a message know what's in the message, even though there may be eavesdroppers in the middle who are able to get access to the encrypted version of that message. Now, a lot of cryptography is actually based on the conjectured hardness of certain problems. Here is an example of one of these. It's called the discrete logarithm problem, and it underlies a lot of systems of modern cryptography. So let's say you have numbers g, a, and p, and there's a particular operation, namely raising g to the power of a modulo the number of p. So doing that forward computation, given the numbers g, a, and p, is relatively efficient even if the numbers g, a, and p are really, really, really large. I mean, it's not as efficient as executing a single assembly language instruction, but in the grand scheme of things, the complexity, the time to run this grows slowly as the sizes of G, A, and P grow. On the other hand, if you are given big A, the output of this operation, together with G and P, inferring little a is believed to be very, very difficult. And as the sizes of these numbers grow, the difficulty grows very, very quickly. So, how can you use this to implement some cryptographic operations? Here's one called Diffie-Hellman key exchange, and it was one of the very, very first cryptographic operations that was introduced way back in the 1970s. So suppose that Alice and Bob each create secret numbers, little a and little b. They send them through this function. So Alice computes g to the a mod p and Bob computes g to the b mod p, and then they exchange those encrypted or those processed versions of the secret key. Now, an eavesdropper could actually observe big A and big B, but we're assuming that the eavesdropper doesn't have access to little a and little b. Now, there's this magic computation that Alice and Bob can now do. Alice can take whatever Bob sent and raise it to the power of her secret key. And Bob takes whatever Alice sent and raises it to the power of his secret key, both mod p. And it turns out that both of those computations will give you the exact same secret number, which now Alice and Bob share that secret, but no eavesdroppers can infer what that secret was without doing a lot of computation. And you can use this as the basis of setting up a key for an encryption algorithm for them to send messages back and forth. Now, of course, to make these practical, the numbers G, A, B, and P have to be really, really, really large. Otherwise, you can just go through a brute force computation. If you used 32-bit numbers for this, you could probably do that brute force in, seconds. If you used a long, in other words, 64 bits for this computation, well, maybe it might take your computer to, a good long while to crack this encryption. But shady government agencies, yeah, they'll totally be able to do it. And so for this to be a useful way of really keeping secrets, we need the numbers involved to be thousands and thousands of bits. And so this motivates multiple precision arithmetic, or big num libraries. They are able to evaluate arithmetic on quantities that are bigger than just a single machine word. And basically, they're going through these arithmetic operations sort of by hand, like you would, except that they're operating not on single decimal digits between 0 and 9. They're operating on chunks that are themselves, let's say, 64 bits long. So the digits, the individual digits, instead of ranging from 0 to 9, range from 0 to 18 quintillion-ish. So there are libraries like this out there, and for this assignment, you're going to implement a simplified version of one of these multiple precision libraries. So our version is called BigInt. It's limited to 32,768 words, each of which are 64 bits long. It doesn't include negative numbers. It doesn't include subtraction, multiplication, raising to powers, modulo. It only really includes the addition operation. So we aren't quite going to be able to do Diffie-Hellman, but instead we have a test client that uses the BigInt library to compute really, really, really big Fibonacci numbers. So if you're not familiar with Fibonacci numbers, first of all, how in the world do you breed rabbits? But second of all, do look up what Fibonacci numbers are. And in particular, notice that they do grow really quickly. They grow exponentially. And so very quickly, in order to compute large Fibonacci numbers, you start needing arbitrary precision arithmetic. So let's look at what the BigInt object is. It is very, very simple. A BigInt is a pointer to a BigInt T is a pointer to a struct BigInt, and a struct BigInt just contains a length and an array of longs. That's it. And the array of longs isn't itself even dynamically allocated. It has some fixed length that corresponds to the number of digits we could possibly be using. So, when you allocate one of these BigInt T's, you allocate, the BigInt T itself is going to be a pointer to a struct BigInt, which you've allocated presumably on the heap. And that contains a length field as well as 32,768 fields, each of which can hold a single digit, where a digit, remember, is actually a 64-bit long. So if the length is 1, we really only care about the first digit. If the length is bigger than 1, then we care about some prefix of all of those digits in the array. And so now how do we do addition on these? So let's say that this is the representation of, a 3-digit number and a 2-digit number that we're adding. Well, we just do grade school addition. We start at the right and proceed all the way to the left, adding individual digits, and also we need to keep track of carries. So let's start here. We'll start at the right. We add this digit consisting of a bunch of 1s and a bunch of 7s, and this is in hex, of course. And we get a bunch of 8s. And notice that these numbers are stored so that the least significant digit is always stored first. So this is little endian storage, if you recall the discussion of little versus big endian. So this is really all we need to do for this digit, and so we move on to the next one. Now, here, when we add the digit consisting of a bunch of 2s and a bunch of e's, we actually get something that overflows 64 bits. It's bigger than we can represent with 64 bits. So the low order 64 bits go into AUL digits 1, and we need to keep track of a carry. And if you look at the BigInt add .c, you'll notice that there is a variable that actually stores that carry. It's called UL carry. So we move on to the next digit. We add the one number that we had at that place with the carry. Again, we get an overflow. We store the result in digits of 2. And now we need to expand the length of the number that we're using for the sum. And we actually do that final addition, which consists of 0, 0, and that 1 carry. And so the result is just 1. And now we need to set the length of the output, and we wound up with 4 digits that end up representing the result of the addition. So that's roughly how the algorithm goes. It really is just grade school addition. So now, what are you supposed to do for part 2? The first thing is we actually have given you a C implementation of BigInt add. So we want you to look at the code, run the code, and figure out how efficient it is. Figure out how much CPU time it takes to compute the 250,000th Fibonacci number. The second part of part 2 of this assignment is now recompile the code, but using compiler optimization. So you pass -d ndebug and -o into the GCC compiler. The compiler is going to think about it a little bit longer, try to generate a better version of the assembly language code. And we want you to see how well it did now, when it was trying to do the optimization. So again, time it, figure out how long it takes to compute the 250,000th Fibonacci number. For part C, we actually want you to figure out where the code is spending all of its time. So if you're going to, put effort into optimizing the code yourself, obviously you want to put effort where it is necessary. You don't want to be optimizing parts of the code that don't matter. And so there's a tool called gprof that'll tell you exactly where the code is spending all of its time. And you'll see more about that in the next lecture. So hint, hint, gprof probably is going to tell you that most of the CPU time is spent in big int add. Well, not surprising. Basically the way you compute Fibonacci numbers is you repeatedly add two numbers together. And so for parts D, E, and F, you're going to be rewriting the big int add function in assembly language. Now, this is, when you do this, you're going to need to make sure that your function that you wrote in assembly language is actually callable from C code, because you're not going to be rewriting the entire program in assembly language. And this is actually kind of how assembly language gets used in the real world these days. People don't write entire programs in assembly language. They write little tiny narrow bits of code that they think they can make run super, super fast. That's all they write in assembly language. And for that to be useful, it has to be callable from code in C, let's say, or other programming languages. So, like I said, this is a common paradigm. You'll see out there people releasing very optimized libraries, sometimes they call them kernel libraries, that accomplish very particular tasks in cryptography, image processing, video, compression, scientific computing, and so on and so forth, where they've taken just the very inner loops of all of these algorithms and rewritten them to run as quickly as possible for a particular hardware architecture. So this is essentially what you're going to be doing in the remainder of part 2. You want to write correct, optimized code. And like we said, if you do a good enough job, eventually you'll actually beat the compiler. So part 2D is going to be a straightforward translation, as in part 1. There's the main big int add function as well as the little helper function big int larger. You'll need to translate both of those, but no other functions. Again, we expect you to use the same algorithm, same logic. Don't optimize yet. Use the same local variables, store them in memory the way we've shown you, and test this code by comparing against the output of the C code. And because we're dealing with really, really, really big numbers, probably a good way of testing is to generate output from both the C version and the assembly language version, and to compare that output using something like diff to make sure that it's identical. Part 2E, probably the code you wrote in part 2D isn't going to beat the compiler yet. So we're going to ask you to start optimizing your code. The first bit of optimization is going to be to use callee saved registers instead of memory for all the parameters and local variables. So don't save anything onto the stack anymore. And then next, for part 2F, we have a couple of specific suggestions for how you can optimize the code further. Now, this is the challenge portion, so challenge portion rules mean we're kind of not going to be able to help you do that. But we are offering some examples of things you may want to try to implement. You can implement the guarded loop pattern that is described in the textbook, chapter 5, section 3.2. You can inline the call to big int larger. That is just, move that code from a separate function directly into big int add, so you don't have that extra function call taking time. And there's a particular instruction, add with carry, ADCS, that can actually help you avoid having to keep track of that carry explicitly in a separate variable. So these are the optimizations to start with. Feel free to implement any additional optimizations. There certainly are ones that you can implement to make the code run even faster. And if you implement enough of these optimizations, it's actually pretty realistic to beat the best version created by the compiler by something like a factor of 2. On the other hand, this is challenging. This is, one of the, if not the most difficult, challenging parts of any assignment in all of COS 217. So this can really be a time sink, but kind of don't let it. Spend a realistic amount of time on it, and if you can't make any further progress, we're not going to think unkindly of you if you kind of stop at any given point. So this is a partnered assignment. You're going to be working with a partner. We ask that you please do find a partner for this assignment. It'll make your life easier, and it'll make our lives easier in grading the assignment. So that's it for now. Please watch the second part of Lecture 20, and there will be more details on this in the upcoming precepts.